In this keynote talk, I will present some of my research on the fundamentals of measurement across the sciences that I explore, unlike many others, using transdisciplinary approaches. Diverse views are taken on measurement. As transdisciplinarian, I regard contradictory views as the breeding ground for new ideas and advancements, because science lives from controversy. Indeed, if we all had the same views, we wouldn't have come together for this conference. Therefore, I look forward to discussing with you. Let me start with an everyday observation. We encounter numbers everywhere. When we buy apples in a shop, we have to measure their weight. The weighing scale gives us several numerical values, one for the apple's weight and one for their price. The weight is measured, but the price is not. The apple's weight, or properly stated their mass, is a quantitative property that they have as physical objects. The price, however, is a financial value that sellers attribute to them and ask us to pay. As an attributed quantitative value, the price is changeable between shops and over time. A kilogram of apple, by contrast, always has the same mass everywhere. In the recent customer satisfaction survey, the shop got a 4-star rating. Online we see the apples rated 4.1 on a 5-star scale. Now, are these rating scales obtained through measurement, like our apple's mass? Or are they socially attributed values, like their price? There are some striking differences. To measure the apple's mass, we must place them on the weighing scale. Their mass is indicated only while they are sitting on the scale. Their price, however, is determined by sellers, who explicitly consider various socioeconomic factors, such as availability and demand. They adapt the kilo price flexibly and even prospectively, and without even touching the apples. Product and customer ratings, in turn, can be generated also in absence of the objects rated, and even from hindsight when they no longer exist. This is impossible for physical measurement. Like the price, ratings involve various considerations, but unlike the price, these are commonly done implicitly and, moreover, in individually varying ways. These observations highlight important points that will help to elucidate basic principles of measurement and fundamental differences to approaches used in psychology that I will explore in this speech. First, I will briefly explain transdisciplinarity, which is still not well known. Then I will introduce the general process structure of empirical knowledge generation. It forms the basis for analyzing the fundamentals of physical measurement, developed in metrology, and for contrasting these with statistics, especially psychometrics, often thought to enable the measurement of mind. Then I will discuss psychology's unique challenges, given the peculiarities of its study phenomena, and show how these make us prone to logical errors and to overlook that statistics is not measurement, as often assumed. Finally, I will show how the basic principles of measurement can be implemented in psychology in epistemically valid ways. First, what is transdisciplinarity? This is a new way of scientific inquiry that differs fundamentally from other kinds of scientific collaborations. In multidisciplinary research, a topic is studied from the perspectives of multiple disciplines. They each contribute their disciplinary knowledge, concepts or methods, yet without aiming at integration. In interdisciplinary research, in turn, different disciplines collaborate on a topic aiming at synthesis and integration. Therefore, concepts, approaches, and methods are transferred between disciplines and integrated through the topic into their disciplinary work. The Latin prefix inter means between, in the midst of. Transdisciplinarity, by contrast, explores topics that can be comprehended only outside of the boundaries of separate disciplines, such as higher-order complexity. Therefore, transdisciplinarity challenges the entire framework of disciplinary thinking and knowledge generation. It relies on disciplinary paradigms but also transcends and transforms them with the aim of creating new unitary frameworks. The Latin prefix trans means across, beyond. Transdisciplinarity explores implicit assumptions and the processes of inquiry established in different fields. It uncovers hidden relations between disciplines and the underlying philosophies of science, as well as necessary differences. At the core of my research is the transdisciplinary philosophy of science paradigm that I have been developed for research on individuals, the TPS paradigm. Research on individuals is a complex field that is concerned with phenomena from all domains of human life. This involves abiotic phenomena, such as individuals' non-living environment, biotic phenomena, such as individuals' physiology and behaviors, psychical phenomena, such as individuals' emotions and thoughts, as well as sociocultural phenomena, such as individuals' social relations and language. These different kinds of phenomena are all merged in the single individual's functioning and development. When we study them in isolation and separate fields, we cannot comprehensively explore human individuals. We need overarching frameworks that enable integrated explorations. Therefore, measurement results must have comparable epistemological validity, thus be justifiably attributable to the objects of research. Otherwise, they can't be integrated across disciplines. This is a main motivation for my transdisciplinary research on measurement. The TPS paradigm is transdisciplinary because it transcends disciplinary boundaries. I integrated concepts from physics, metrology, biology, medicine, psychology, and social sciences and transformed their core ideas into new, overarching concepts. This integration was possible on the philosophy of science level by making explicit the most basic assumptions and rationales of inquiry used in different fields. This revealed relations and differences in their underlying ontologies, epistemologies, and methodologies. The TPS paradigm is a meta-paradigm because the concepts were derived from various disciplinary paradigms. I integrated them on higher levels of abstraction in 3 unitary frameworks that build coherently upon each other. Transdisciplinary research is challenging in many ways, starting from our disciplinary jargon, the terminology with which we have learned our science and which varies between scientific communities. Particularly challenging are jingle-jangle fallacies, when the same term refers to different concepts or different terms to the same concept. This can lead to misunderstandings across disciplines. In my primate and personality research, I elaborated conceptual relations between psychology and biology, as well as between human and animal research. I had long conceptual debates with colleagues from animal biology. We all thought we were talking about the same. I will never forget how, after months of intense written exchange, I realized that the terms state and trait have opposite meanings in our fields. In psychology, states are temporary and traits more stable. In biology, it's the exact opposite. Either linguistic choice is justified, but when such differences go unnoticed, we're talking at cross purposes. Later, I made similar experiences when I started to scrutinize psychometrics and other statistics used in quantitative psychology, in which I have been trained for many years. This was the only measurement jargon that I knew. When I explored the underlying concepts more deeply from transdisciplinary views, I recognized here as well disparate meanings for the same term. But in this case, they are used within the same discipline, even by the same author and in the same text, and I found them even in my own writings. As authors, we can flip easily between different meanings because we know what we want to say. This makes it so hard to identify inconsistencies in our own writings. It is difficult to take a meta-perspective on our scientific language while thinking also about the research itself, because we are thinking research through language. In quantitative psychology, these disparate meanings often entail conceptual confusions and even logical errors, for reasons I will explain in this speech. So terms matter. It would be desirable if we all used terms in the same ways, but this will never happen, given the many disciplinary cultures established in our fields. To make research accessible to others and avoid misunderstandings, especially logical errors, we should explicate the specific meaning that specific terms have for us in our research. This requires precision in scientific description. And that's what I want to do here briefly, for some basic terms that I know are understood differently by colleagues here at the conference, given our backgrounds. First, as we are discussing measurement across sciences, the term science. I use it in its broad meaning, as reflected in the Latin scientia and the German Wissenschaft, which covers all fields that generate knowledge by means of systematic, rigorous, and method-based inquiry, unlike the narrowed Anglo-American meaning. The term phenomenon I understand in its ontological meaning, defined by Nikolai Hartmann as that what is intended to be studied, which may be anything that exists, and not in the Kantian epistemological meaning. Quantification denotes in metrology the outcome of a measurement process, as Luca Mari and others highlighted, emphasizing the distinction between both. In psychology, it is used indiscriminately for both process and outcome, as is the term measurement. Here I use quantification for processes to generate quantitative values that do not meet the criteria of measurement, an important distinction, as I will show. And I refer to the outcomes of both kinds of processes as quantitative values. I will clarify further terms later. Using these fundamentals, I will now take a transdisciplinary perspective and outline the general process model of empirical knowledge generation developed by Robert Rosen, a mathematical biophysicist and theoretical biologist. He pioneered relational science, which is concerned with the mathematical modeling of systems of higher order complexity, such as the functional organization of life. For modeling, he used category theory. Unlike quantitative mathematics, this general mathematical theory is not concerned with measuring and calculating quantities. Instead, it formalizes abstract structures and relations between mathematical objects and their qualitative transformations. It belongs to pure mathematics, sometimes called qualitative mathematics. Rosen also modeled the processes by which living organisms selectively perceive specific parts of their environment and make sense of that information, thus how they generate knowledge empirically. Scientific knowledge generation is a special case of these fundamental processes. Rosen modeled these processes as relations between mathematical objects, also called mappings. The object here on the left models the specific part of the world that we aim to explore. It comprises our natural objects of research, such as our apples or an individual. This is the real system under study. It is mapped to the explicit scientific model here on the right, that we create to study the information that we obtain about that real system. This formal study system serves as a surrogate that we can explore in ways not possible with the real system itself, such as mathematically. Rosen conceptualized empirical knowledge generation as a coherent system of modeling relations, each within these two different systems and back and forth between them, here depicted as arrows. Now, what do these different modeling relations involve? In science, when we perceive some events as changes, we attribute to them some causes, which we cannot directly perceive. We can only presume their existence and causal relation to the changes observed, here shown as arrow 1. To explore these presumed non-observable causes in the real system, we must encode its observable changes in our formal system, such as in variables. These raw data symbolically represent selected information about the real system. Through this encoding, we establish mappings between real and formal system. This is the data generation, here arrow 2. Within the formal system, We can then manipulate the encoded information using data modeling techniques, such as mathematical ones. This is the data analysis. Here, error 3. We must use our preliminary knowledge of the real system to decide which specific formal manipulations might be appropriate to study the information encoded. From this, we obtain an implication, thus some analytical result. When we believe that our formal model is appropriate and its internal relations may correspond to those that we presume for our real system, then we have to relate the formal results back to that real system. Thus, we must establish a decoding relation, here arrow 4. For this, we must interpret the formal results with regard to non-formal events that may occur in our real system. Only then can we compare the results with new observations to test how well our formal model may represent the presumed causal relations in the real system and help to explain its observable changes. Through reiterative cycles of observation, encoding, formal modeling, decoding, and retesting, we can stepwise develop a coherent system of interrelated modeling relations. Thus, Rosen conceptualized empirical knowledge generation through relations within and between mathematical objects and the relations between these relations. This highlights some key points, often not well considered in empirical inquiry. First, the natural system under study and the surrogate model that we construct for studying it are of different kind, real versus formal. The mappings established between them, the encoding and decoding relations, arrows 2 and 4, therefore involve transformations that cannot be derived from within either system. Thus, these relations are independent of both systems. Specifically, in the real system, we can make potentially unlimited amounts of observations. These must be mapped onto the closed sign system that we use as its formal model, such as some variables. That is, we must make decisions about what to represent and what not, and also how to represent it. Therefore, encoding, the data generation, is highly selective and reductive, a crucial point later elaborated also by Bas van Fraassen in his book Scientific Representation. Decoding the inverse relation from the formal system back to the real system, here arrow 4, is a delicate process as well, because we obtain the results through formal manipulations, which are not possible in the real system itself. Therefore, we must now transform the formal results meaningfully with regard to our real study system. This requires interpretation. The epistemic necessity of transforming back and forth between real and formal system makes the entire modeling process prone to methodomorphism. For example, during the decoding, our mathematical models can impose structures onto our results. If we erroneously attribute these method-based structures to our objects of research, this may unintentionally influence and limit the concepts and theories that we develop about these real objects. Rosen's process model highlights that our interpretations and decisions are crucial in the modeling process. Indeed, only the execution of operations in the formal system, such as statistical calculations, are free of subjectivity. However, the specific formal model is not a given, but chosen by us, based on our preliminary, incomplete knowledge of the real system. The formal system is thus subjective in many ways as well. In sum, Rosen's system provides the epistemological fundamentals for using abstract representations of observable regularities to investigate their possible non-observable causes. It models the necessary process structure that epistemically justifies the attribution of our results to our objects of research. Rosen's mathematical model of empirical knowledge generation also underlies measurement as conceptualized in metrology. Here as well, the problem is that many physical properties are not observable. In the early stages of inquiry, a property's relations to observable changes, such as in interactions with possible measuring instruments, were still unknown. These relations can be established only using a validated instrument. But to first establish a measuring instrument, we must know these relations. This creates epistemic circularity. So how can we justify to assume that a specific procedure does indeed allow us to measure a specific physical property? This concerns the problem of measurement coordination. Metrologists such as Luca Mari, Paolo Carbona, and Dario Petri, as well as philosophers and historians of science, such as Alessandro Giordani, Eran Tal, and Michele Lucchetti, analyzed in detail the epistemic processes by which physical measurement procedures were developed. This problem is tackled with a coherentist approach, thus, by establishing a coherent system of interrelated modeling relations as described by Rosen. It starts from initially just presumed causal relations in the real study system between the measurand, that is the non-observable quantity to be measured, and the observable instrument indications that we obtain from their non-observable interaction, under defined conditions, here arrow 1. To explore their unknown relations, we must establish unbroken, documented, and thus traceable relations, first to the raw data in the formal system, then within that formal system, and finally from its formal outcome back again to the real system, here arrows 2, 3, and 4. Then we can compare the decoded results with new observations and restart the entire process cycle of observation, encoding, formal modeling, and decoding. In many epistemic iterations, this cycle of interrelated modeling relations is passed through over and over again, whereby the formal model is re-coordinated to more reliable empirical indications. This enables more precise tests of predictions, more refined and more standardized methods and instruments, and so on. That is, through iterative feedback loops, we can establish systematic epistemic justification that we have developed a coherent system of coordinated mapping relations, each within and between the real system and our formal model of it. Ha-Seok Chung's book, Inventing Temperature, traces the enormous challenges that this involved for developing thermometers and our knowledge of temperature. Measurement coordination also involves the problem of how to justify that we assign specific quantitative values to specific properties under defined procedures, such as why assigning boiling water a temperature of 100 degrees Celsius but 212 degrees Fahrenheit, and that this always indicates the same temperature. As Rosen's model highlights, quantitative values are just formal representations of information. As such, they are generally arbitrary and often established by decree. The conventionally agreed quantitative meanings of physical measurement results are codified in the International System of Units. This requires calibration, a process by which the quantitative values assigned in a measurement procedure are related to the same traceable reference standard, here symbolized as an artifact, but most are meanwhile defined by natural constants. In global calibration networks, all instruments are connected in unbroken documented ways to the same reference standard. This integrates its known quantity into the coordinated system of interrelated modeling relations that are established for a given measurement procedure. In this way, all unknown quantities, such as our apple's mass, are measured through comparison with a known quantity, such as that of the standard quantity, kilogram. That's why we can all understand how much that is, everywhere in the same ways. To ensure universal consistency and compliance, each instrument's deviation from the reference standard is documented to determine uncertainties and errors, so that future results obtained from an instrument can be corrected for systematic effects. That's why we can put our apples on different weighing scales and get the same results, within specified margins of error and uncertainty. Now, what are the most basic principles of physical measurement? Let's take a transdisciplinary perspective. We have seen that measurement is a documented process structure that coherently relates a formal with a real system, both theoretically and empirically. On the theoretical level, we need some at least preliminary knowledge of the real system, including some ontological assumptions on its fundamental nature. From this, we derive epistemological presumptions that guide our decisions and interpretations when we develop a measurement procedure. Thus, measurement is a theory-laden process. On the empirical level, we must implement unbroken connection chains between the unknown quantity to be measured, such as our apple's mass, and a known reference quantity with which the instrument is connected through the global calibration network, such as the standard kilogram, and the measurement result, expressed as a quantitative value, here 744 grams. That's why we must put our apples on the weighing scale to measure their mass. This process structure allows us to trace back the measurement results to the measurand's unknown quantity. I call this data generation traceability. And to the known quantity reference. I call this numerical traceability. That's a transdisciplinary generalization of the metrological traceability in calibration networks. Procedures that build on these two methodological principles meet two criteria. First, epistemically justified inferences from the results to the real quantities to be measured. That's also called object dependence in metrology. And two, the results unambiguously interpretable quantitative meaning regarding that real quantity. This means we can be sure that these 744 grams refer to our apples and only to them, and that this does not also depend on who is weighing them, how often or where. And we can all understand how much that is, everywhere in the same ways. It is this theoretically and empirically defined process structure that establishes the epistemic authority of measurement and that justifies the high public trust placed in it. And because of this, I advocate for a criterion-based definition of measurement and against a soft or wide definition for psychology. Because just changing the definition doesn't establish but only undermines its comparability across the sciences. A criterion-based definition, by contrast, allows us to scrutinize the epistemological fundamentals of the procedures used in different fields and to pinpoint commonalities and differences. It also informs principles, such as the two traceability principles that can guide the development of discipline-specific analogues of measurement that appropriately consider the peculiarities of other fields' study phenomena. Therefore, I define measurement as a structured process that first epistemically justifies that we attribute to an unknown quantity to be measured, to a second, a specific quantitative value that is unambiguously interpretable regarding that quantity. This also shows measurement is about quantities. Some argue that quantitative results are neither necessary nor sufficient for measurement, and that its defining feature is its process structure and not its results. This was also Robert Rosen's view. I agree that quantitative results alone cannot define a process as measurement. Therefore, I distinguish quantification as a process for generating quantitative data that does not meet the criteria of measurement, as I'll show later. But if we called all epistemically justified processes measurement, then this would apply also to text analysis and other so-called qualitative methods that rely on traceable and iteratively established relations between the objects of research and our formal models of them. We already have established terms for this, such as scientific representation. Sure, we could call any scientific inquiry measurement, but then we would have to distinguish qualitative from quantitative measurement, which is an erroneous distinction, or invent new terms. This only shifts the problem. It doesn't solve it. Measurement has advantages over mere nominal categorization because it enables more sophisticated analysis of objects and their relations. It allows us to not just categorize objects by their specific kind, their quality, but additionally to differentiate between their divisible instances, their quantities. My line of research builds on Nikolai Hartmann's ontology, in which quality and quantity are objective, fundamental dimensions that structure all levels of reality. For Hartmann, quality and quantity are paired categories. That is, they are defined in relation to one another because neither can exist in isolation. Every concrete entity possesses both qualitative structures, the what it is, such as mass, length, or time, and quantitative structures, the how much of this, such as degree or magnitude. One cannot have pure quantities. Any quantity is always a quantity of something, a specific qualitative property. Therefore, Hartmann argues that the world's qualitative aspects cannot be exhaustively reduced to mere quantitative relations. And because any quantity must inhere in a specific quality, comparisons of quantities, such as more or less, make sense only if their qualities are of the same kind. It makes no sense to say an object is longer than it is warm, but not as heavy. This homogeneity is what grounds measurement. These points are particularly important for psychology, as we'll see. Now, let's look at statistics. Some differences stick out immediately. In physical measurement, every method is specific to one single physical property. We can use a thermometer to measure. We cannot use a thermometer to measure also mass and time. But we can use the same statistical methods, such as t-tests or latent variable modeling, to analyze information about any kind of phenomenon. Measurement, as we have seen, is the epistemically justified and coherent grounding of a formal model in a specific part of reality. Statistics, by contrast, concerns the analysis of data sets regardless of how the data have been generated and what these are meant to represent in the real world. That's why statistics builds only on theories that define the workings of the analytical operations performed, such as probability theory, but not also on the theories of the objects of research as required for measurement. Statistics neither conceptualizes nor empirically establishes traceable relations between a real and a formal system. It is concerned only with the modeling relation, here arrow 3, but neither with data encoding, arrow 2, nor with decoding, arrow 4, nor with the internal relation of the actual study system, here arrow 1. Hence, there is an epistemic gap between a statistical model and the real system to be studied. This obscures their epistemic distinction and leads to their frequent confusion, which entails logical errors. For example, for statistical analysis, a term for the quantity to be measured, the measurand here on the left, is not required. And indeed, it is unknown to most psychologists. They focus on truth scores, which are estimates obtained in the formal model here on the right. Truth scores are often mistaken for the measurands, thus for the real unknown quantities that we want to determine. But these are neither conceptualized nor empirically traced in a statistical modeling. Another example. In latent variable model, raw data are called observable or manifest variables, from which so-called non-observable or latent variables are modeled, which are thought to represent the object of research, such as intelligence. This common jargon leads to confuse the modeling relation 3 here on the right with the encoding relation 2 here at the top. But the latent variables are modeling formal structures that statistically underlie the manifest variables, here on the right. Their interpretation as non-observable and underlying leads to the frequent reification of variables by mistaking them for the real objects of research, such as persons' abilities that underlie their test performances, here on the left. Variables form part of the formal system. We create them to encode information, but we neither observe variables nor do we measure latent variables as often stated in psychology. One cannot measure measurement results. These problems also occur in psychometrics, a specialized field of statistics focused on measuring the mind and its unobservable phenomena. Psychometrics provides sophisticated methods to discriminate well and consistently between cases, such as to compare student performances across countries, as in the PISA tests, or to select applicants for a job. For such applied purposes, tests in which everyone gets the same result are uninformative. Psychometric instruments, such as intelligence, knowledge, or personality tests, are therefore designed by selecting tasks or rating items that consistently yield results with structures that are statistically desirable and practically useful, such as norm distributions that distinguish well between high and low performers. I call this result-dependent data generation and instrument development, as opposed to the object-dependent processes required for measurement. Because of this, quantitative meaning for psychometric scores must be created statistically for each given sample. The IQ score, for example, indicates individuals' deviation from the age group's average, which is set arbitrarily to 100. And one standard deviation is set to 15, so that 68% of the sample fall between 85 and 115. Therefore, the same test performance shown by persons of different ages may be assigned different IQ scores. Thus, the IQ score does not inform about their actual performances, but only about relative differences within their age group. IQ scores generally increased in the 20th century and recently decreased again. That's why IQ scores tests must be regularly renormed to keep the average at 100. Metrologists, by contrast, do not change the length of the standard meter just because people become generally taller. We see psychometrics is aimed at fundamentally different epistemic purposes than measurement. It builds on a pragmatic utilitarian framework to generate quantitative values that are useful to differentiate and compare cases. For these pragmatic purposes, statistics is indispensable. Instruments and models are built on psychometric theories like item response theory as in Rasch models or other classes of latent variable modeling. These allow for modeling test responses by the probability that persons solve a task correctly as a function of person ability and item difficulty, here on the right. Therefore, the correctness of standardized test responses is encoded, often in binary data. But psychometrics is not aimed at exploring how the test performances, here on the left, are generated in the first place, using which specific, qualitatively different abilities and in what combination. Psychometrics does neither rely on nor inform theories of the real system. Instead, abilities are considered only on very abstract levels, simplified into a single, unidimensional parameter here on the right. That's pragmatically useful and allows for applying psychometric models to all kinds of abilities in the same way, typical for statistics, but unlike measurement. But because of this abstract simplification, it is impossible to decode, thus to interpret the statistical truth scores of the person parameter regarding persons' actual mental abilities. Their interrelations are neither conceptualized nor empirically established as required for measurement coordination. We see, Psychometrics is focused on the formal system, here on the right. This is justified and valid for its specific purposes and uses. Psychometrics has pragmatic validity, as Samuel Massick, Michael Caine and others emphasized. It has predictive power, yet without providing explanation. Danny Borsboom, Anna Alexandrova and others aptly called its rational utility above truth. But psychometrics is neither concerned nor does it establish unbroken traceable relations both to the real quantities to be measured in individuals and to known reference quantities. It does not adhere to the principles of data generation traceability and numerical traceability that underlie measurement. Therefore, psychometrics does not establish epistemic justification to draw inferences from the results to the abilities tested. Intelligence tests do not measure intelligence, as often claimed. They provide comparative summary scores of individuals' performances, often across several, qualitatively different subtests. These abstract scores have quantitative meaning only within specific samples and tests, but not regarding the mental abilities themselves that underlie individuals' test performances. Thus, psychometrics has no epistemic validity, and therefore cannot be used to study mind, such as which specific intellectual processes may interact in what specific ways to enable a specific test performance. Psychometrics enables pragmatic quantification, but it does not meet the two criteria of measurement. Still, psychometrics is commonly believed to enable the measurement of mind, as its very name shows. This interpretation confuses two incompatible epistemological frameworks: the pragmatic utilitarian, that is implemented theoretically and empirically, and the realist framework, that underlying the physical measurement that psychometricians commonly invoke in their interpretations. This again confuses formal and real system and entails logical errors. These errors, however, are masked by psychology's unique challenges that arise from its study phenomena's peculiarities. In psychology, we study individuals, thus systems of higher order complexity. They feature peculiarities not known from the properties of abiotic nature that are measured in metrology. I'd like to mention just some. As we have seen, for physical measurement, experimentation is crucial to enable the reiterative testing required for coordination and calibration. For example, thermometer developers use defined heating procedures to vary temperature. In psychology, we cannot experimentally control and vary our study phenomena, such as individuals' processing speed, beliefs, or reasoning abilities. At best, we can vary some experimental settings, but the study phenomena themselves do vary within and between individuals, contexts, and times. This is because from interactions between processes, novel properties emerge on higher levels of organization. These higher-order properties can feed back to and change the lower-level processes themselves from which they emerge. For instance, from individuals' interaction, language emerged gradually in human communities. Language, in turn, mediates and shapes how we perceive, think, and categorize the world. This enables novel individual abilities and ways of social interaction, from which in turn more complex language structures emerge. Such dynamic multi-level feedback loops lead to processes of continuous change and irreversible development. This complexifies the relations between levels of organization, in that the same process can generate different outcomes. For example, the same intention can motivate different behaviors. Thus, there are one-to-many relations between underlying causes and observable outcomes. We also find many-to-one relations, in that different causal processes can generate the same outcome. For example, different intellectual abilities allow for solving the same task. When we consider many processes and outcomes at once, we must conceptualize many-to-many relations. Thus, in living systems, Causal relations are complex, varying, and changeable. This precludes inferences from observable changes to possible non-observable causes that universally apply to all individuals. Metrology, by contrast, is concerned solely with unchanging relations of abiotic properties. For instance, kinetic energy and temperature are always related in the same ways under defined conditions. These unchanging relations first enable measuring instruments, natural constants, and internationally standardized systems. We can place our apples on the weighing scale countless times. This changes neither their mass nor their interaction with the weighing scale. But humans memorize and learn. They do not interact with the same instrument in always the same ways. Humans are thinking agents with personal aims and values. They have intentions, beliefs, and sociocultural views on the world. Customer ratings, such as of apples or shops, therefore do not provide information about these objects per se, but about people's judgments of them. These are done implicitly and vary individually. Unlike metrology, psychology studies not just observable phenomena and their possible causes in themselves. Instead, it explores individuals' subjective and intersubjective interpretations, attributions, appraisals, and explanations of what they can observe, as Wilhelm Wundt already highlighted. These complex phenomena are studied as constructs. As the term indicates, constructs are constructed. They are mental construals. As products of mind, constructs are abstractions. Abstractions allow us to filter information about complex phenomena by emphasizing in our minds some details and de-emphasizing others, depending on their relevance and meaning for us. Therefore, I define a construct as a conceptual system that refers to a set of entities, the construct reference, that are regarded as meaningfully related in some ways or for some purpose, although they actually never occur all at once. We only think of them as a joint entity. Intelligence refers to a broad range of qualitatively different abilities that we can never use all at once. Thus, constructs differ from concrete concepts like that of apples, in that they have multiple heterogeneous reference. Thus, constructs are multi-referential. Inevitably, the specific construct reference being considered vary. No psychological construct is without disagreement about its reference, such as which specific abilities belong to intelligence. That's why there are so many overlapping constructs. Thus, constructs allow us to mentally handle qualitatively different reference at once and to simplify them in ways that matter to us. This is extremely useful to navigate complex worlds. All humans develop constructs to make sense of regularities that they perceive in their everyday lives, as George Kelly emphasized. These everyday constructs are important objects of research in psychology. As scientists, we also develop constructs as scientific means to summarize and categorize regularities in our objects of research on more abstract levels. Scientific constructs are, or should be, explicitly defined and more elaborated than intuitive everyday constructs. Still, they are of the same kind. Rosen's system reminds us to clearly distinguish a construct, thus a mental model, here on the right, from its diverse reference in the real system, here on the left. And here it is getting tricky, because psychology studies human minds. This blurs the distinction between everyday constructs studied as objects of research, here on the left, and the scientific constructs used as our means of inquiry, here on the right. This requires nested modeling relations between scientific constructs and their reference, which in turn may be constructs themselves, each with their own reference. Scientific constructs belong to the formal model, and therefore cannot be measured. One cannot measure a formal model or its result. We can measure only their reference in the real system, if these are amenable to measurement. As these are qualitatively diverse, they often require different methods of inquiry. Thus, constructs are abstractions of heterogeneous qualities. Therefore, they cannot feature divisible properties, thus quantities in themselves. The common claims that we could measure intelligence, personality, creativity, reading comprehension ability, well-being, happiness, and so on, confuse the formal system with the real system by turning an abstraction into a real object. This common reification is promoted by language. Language is a complex sign system. A sign involves a tangible physical carrier called signifier, such as a written word, that in our minds stands and refers to something else, its referent. Thus, our mental model establishes a word's semantic meaning. We can use a word to refer to indefinitely many particulars of its referent. The word apple refers to all apples that may exist. Thus, words are abstractions. That's why words can refer to objects even in their absence. This referential function of language is built into its semantics and internalized in our minds. Here we see again a system of interrelated modeling relations that are nested within each other. On the right, we have the meaning, a mental model that refers to specific parts of the real world, its referent. Here on the left. To communicate with others, we create tangible signifiers here at the top. In our mental models, we jointly ascribe to these signifiers shared meanings, and we link these through conventions to specific reference in the real world. In our native languages, we are doing all this intuitively and with ease. When using language, we do not perceive our words just as tokens of the reference for which they stand, but as these objects themselves. This obscures the inherently referential function of language. Therefore, we often forget that semantic relations are just in our minds, linking our words and thoughts seamlessly with the objects to which they refer. In everyday life, we therefore easily confuse the world as it is with the world as it is thought about and described. Scientists as well tend to forget that the abstraction of something is not that something in itself. The construct is not the same as its reference, and the data and variables are not the study phenomena for which they stand in our formal models. I call this confusion scientists' cardinal error, because it blurs the epistemically necessary distinction between the objects of research and our means for exploring them. This error occurs especially around language-based methods, such as rating scales, psychology's primary method for generating data, quantitative data, thus for establishing the encoding relations between real and formal system. Specifically, when their built-in semantics, that is, descriptions of the study phenomena and rating scales, are confused with the phenomena described, then judgments of verbal statements are easily mistaken for measurements of the phenomena described. I studied empirically how ratings are related to measurement-based observations of behavior, and how people actually understand and use rating scales. I also identified 12 problem complexes in their underlying epistemology and methodology. That's a 20-year line of research, so I can outline here just a few key points. For ratings, the study phenomena are described in verbal statements called items. Their wording is often more abstract to be applicable to more diverse study phenomena and contexts, yet less specifically, thus to cover a construct's multi-referential meaning more comprehensively. Therefore, items often have broad semantic fields of meaning, as shown here in 112 persons' collective interpretations of the item tends to be lazy. The percentages indicate frequencies in the sample. Importantly, no rater considered the entire semantic field. most reported just 2 of these heterogeneous meanings. So, while some considered poor contribution and quality of work, others considered unhealthy food habits, and still others not keeping deadlines or being disorderly and messy. The specific phenomena to which raters refer an item establish its empirical semantics. When raters implicitly consider different meanings for the same item, thus different study phenomena, the encoding of information in the rating data are based on many-to-one relations of unknown kind. This entails a first break in the data generation traceability required for measurement. When researchers then interpret the rating data, thus the encodings in item variables in the formal analysis, they can rely only on the item's broad semantic fields of meaning, their dictionary definitions, thus their built-in semantics, of which each rater, however, considered just a fraction. This entails a second break in the data generation traceability. Analysis with language algorithms show that psychometrically modeled structures derived from rating data largely reflect the scale's built-in semantics. Thus, the results are largely due to the instruments and not the objects of research. The semantic structures in our languages reflect lay knowledge, such as everyday constructs. As abstractions, constructs also involve subjective and intersubjective appraisals, such as social valences. In my primate research, I contrasted ratings with time-based measurements of behavior, such as durations measured with computer-based encoding live or from video. This species here showed in their behaviors no sex differences apart from 2. Males were more dominant and more aggressive than females, here highlighted in blue. This reflects their egalitarian social system led by larger dominant males. But when students, keepers, and researchers rated these same individuals in the same behaviors on standardized scales, they implicitly attributed to them numerous sex differences that reflect human gender stereotypes. Time-based behavioral measurements also showed that individuals who bite more often do not also show other aggressive acts more often, unlike slap, chase, or threat. Ratings of these behaviors, however, are typically correlated. Thus, they reflect likeness in semantic meaning, rather than actual co-occurrence likelihood of the phenomena described. Raters are asked to indicate their judgment on a scale of a few verbal answer categories that are meant to describe degrees, such as of agreement with an item. These verbal categories are then assigned quantitative values, always the same for all items, no matter which phenomena they describe. Here on the left are time-based measurements of 2 behaviors, each shown by 3 individuals. We can see that behavior A generally occurs more often than behavior B. Thus, to rate these individuals on the scale here on the right, raters must encode a broad range of quantitative information about these behaviors flexibly into this narrow, fixed range of answer categories. They can do so only by constructing for the same scale different quantitative meanings regarding the study phenomena. This fundamentally contradicts the numerical traceability of measurement. I also asked raters why they chose a specific answer box for their rating. Here are the reasons of 78 persons for rating someone on film. Most are qualitative and rather trivial, and rarely ever quantitative. Also, raters chose the same answer box for different reasons, and they had different reasons for choosing the same answer box. Still, these are always assigned the same quantitative values. How raters interpret and use rating scales matters in the real world. Health researchers ascertained that changes in patients' self-ratings, such as pre-post treatment, often cannot be fully explained by actual changes in their condition. This questions the validity of ratings for evaluating clinical theories, treatments, and therapies. Analysis revealed very nuanced considerations that change over context and time, leading to pronounced response shifts, as Femke-Truyens and colleagues and many others showed. Patients' interactions with the verbal scales also changed their interpretation and use of the scales, and even how they evaluated their own health problems. Thus, patients' interactions with the instruments changed not just that interaction itself, but also their appraisal of the object of research. None of this happens when we are weighing apples. The numerous response shifts that occur in health-related ratings highlight the varying, changing, and contextual nature of psychology's study phenomena. Therefore, we cannot make inferences from observable changes to possibly underlying non-observable causes that apply universally to all individuals and across all contexts and times, as this is possible in metrology. For epistemically valid research, we must establish unbroken, documented relations that allow us to trace our data and results back to the phenomena under study. To establish a coherent system of modeling relations, data generation traceability and numerical traceability must be established. In human research, this requires that we enter into epistemic dialogue with our participants to inquire their views on the study phenomena and how they interpret and use our instruments, as Leah McClymans showed in patient-centered measurement. Much is still to be learned about these complex processes and thus ultimately what our psychological data may actually refer to regarding our study phenomena. Language-based AI now provides efficient means to analyze people's views expressed in their own words, unrestricted by predetermined rating scales with their problematic epistemological and methodological foundations. I showed that psychology's complex study phenomena and language-based instruments are multi-referential and therefore rich in interpretable information. In metrology, by contrast, information is conceptualized only as the outcome of measurement in the formal model. Metrological concepts cannot account for different interpretive perspectives that researchers and participants alike can flexibly and intentionally take on the same object of research and the same instrument. These are of no interest to metrology, but essential for psychology. Therefore, metrological concepts cannot be applied to psychology as directly as increasingly suggested in interdisciplinary approaches, but on higher levels of abstraction, using transdisciplinary approaches. The basic principles underlying metrological frameworks can be applied meaningfully to psychology and in ways that appropriately consider the profoundly different nature of its objects of research. I brought together and opened up many lines of thought to critically reconsider the common view that statistics such as psychometrics, as well as standardized rating scales, could constitute psychology's way of measuring its study phenomena. I have shown that epistemically valid research in psychology is far more complex than so far considered. I look forward to seeing new lines of research that further explore these promising new directions. Thank you for your attention.